Linearizing data is taking data that looks like this and turning it into data that looks like this so that we can use this equation here. Now understand that we cannot use that equation on a curved line. This is the equation for straight lines. So I'm kind of already expecting that you can use the slope-intercept form of an equation. But don't skip to another video here if you already know this. You're supposed to already know this. So we're going to be able to use this equation by after we tweak the data to turn it into this. So let me just make sure we're all on the same page here. I'll show you the one example here. But if we have this data here described by this equation, I could take 4 and multiply it by 3, add 7, I get 19. So 4 times 3 plus 7 is that. And we get a nice straight line. But if I calculate rise over run, it rose 30, it ran 10, the slope was 3, crosses the y-axis here about 7, so that's the slope and that's the intercept. And we'll just do it here. Maybe I didn't know the equation, but I did have the data. I could take that line and find the slope, rise, and run. Looks like the slope is -2. The crosses the y-axis at 5. So if I know the slope and the intercept, I can find the equation. It's y equals -2x plus 5. Okay, I hope I haven't done anything new for you there. But let me come back here. This data here was beautiful data. All the data points fit in a nice straight line. But when you do an experiment, sometimes things are messy. Sometimes your measurements are off a little bit because you had an error in your measurements. Okay, so let's say this data represents an experiment where we had 10 different physics students measuring how fast a car was traveling. And one physics student measured that for 5 seconds and found the car went 10 meters. Another student measured for 25 seconds and found that it went 60 meters, and so on. Okay, but everybody got a different set of data, and we're graphing that data, and we want to figure out how fast was that car really going. In this example here, we kind of expect that in no time it should go no distance. So we do expect that it's going to go through the origin. So I've got that data point up there, and that seems like it's kind of about right. So I could find the line that goes through there, and I can find the slope of that. And the slope is y2 minus y1 over x2 minus x1, or the change in y over the change in x. So it rose 150, it ran 45, and that would say that 3.33 would be the slope of that line, or distance over time, how fast that car was traveling. Now, we did do that, but that would be a lousy way to figure out how fast that car is going, because what happened was we had 10 different students measuring how fast that car was traveling, and we ignored 9 of those students and only looked at one data point. And we put all our eggs in the basket asking that one student to measure that. So that's not going to be the way that we're going to find the speed of that car. What we probably want to do is use a straight edge, and we're always allowed a straight edge on tests and the exam. So what you would do is you would kind of eyeball it. You would take your best estimate, get some data points above, get some data points below, but draw that line there and try to do your best to get the best average of those data points. Some above, some below, but just kind of the best average. And then we don't have to, that line didn't have to go through any of the data points, but we can look right there, and there's where that line crosses nicely. It looks like it crosses at 50, 150, so we can find the slope, change in y over change in x, and that looks like how fast that car is traveling. A different answer than we got here. All right, there's still yet a better way. if we're doing this on a spreadsheet, we could right-click on a data point. When we right-click on a data point in Excel, we have the option to add a trend line. If you're in Google Sheets, then you have to go into the setup, and you're going to have to hunt around a little bit, but it is there to add a trend line. We have different options for lines. It already defaulted to be a line, so linear, but it could have been an exponential relationship, logarithmic, polynomial, power, or a moving average. In this video, we're going to go back and we're going to look at exponential and power relationships. We're going to focus in on linear, power, and exponential. The other thing I did in this screen is I clicked that box and I set the intercept to be 0 because I knew it should go through 0. The other really neat thing is we can check the box to display the equation on the chart. So when I hit close there, it will put that line there, that red line, which is a little different from what we guessed. Not bad, but it did the absolute best fit for that. And so because this is on the x-axis and this is on the y, that number is going to be the slope, which again was different than those two. But that would be our absolute best way of finding the speed of that car given this data. Another way students could do that is by taking the velocity that each student measured. Distance divided by time is velocity. This distance and that time, this velocity. And you could have found a simple average by just finding the average of all those numbers. And we see we get a different number. So which way is better, this way or finding the average? The trend line is your best method. The reason is, over here when we found the average of those numbers, every single student weighted the same in the calculation of the average. When the computer does it and calculates the line of best fit, students that were further away from the line of best fit, they didn't count as much. It really takes a very detailed approach to get the best fit here. So a simple average isn't nearly as good as finding the slope of the line of best fit. So try to remember that. So if we could tweak this data, turn it into a straight line, then we could find the equation of that line by using the slope and intercept. Okay, so here's what we're going to do. Instead of graphing x versus y, we're going to graph x squared versus y. What that does is instead of graphing 10 here, we graphed, let me say it this way. Instead of graphing 10 comma 500, we graphed 10 squared comma 500. And instead of graphing 5 comma 125, we graphed 5 squared comma 125. What we did is we tweaked all the data. So this data point here got shifted to here. This data point got shifted all the way over here. Because that curved line can get straight if we move these further to the right than we moved those. It would stretch that out into a straight line. And for now, we're just guessing at what we got to do. By the end of this video, I'm going to show you how to take away the guess and get that answer right in there. Okay, so but we did find that graphing the x squared and the y's turned it into a straight line. And now that we have that straight line, this data follows this form. So we can find the slope of that. Looks like it went from 0 to 500 as a rise, went from 0 to 100 as a run, so it looks like the slope is 5. And in this graph, the data goes through 0, so the intercept is 0. Okay, we could find the equation of this line, but we're trying to find the equation that described our original data. Let me just remind you of this. If this is what we graph on the x-axis and it gets multiplied by a number and adds a number, we would get the number that goes on the y-axis. But we didn't graph x on the x-axis, we graphed x squared on the x-axis. So that is what we graphed on the x-axis. We multiplied it by the slope, which was 5, and then because the intercept was 0, we just added 0. That is the equation that describes this data. Because if I take, say, 2 and I square it, if x is 2, I square it, I get 4. Then I multiply by 5, I get the point 2, 20. If I do this one here, 10 is x, so 10 squared is 100, times 5, looks like y is going to be 500. So we had to linearize this data. We had to tweak the x values to turn it into a line so that we could find the equation of that line. Let's do it again here. Now I played with this and I came up with that we should graph not x versus y, but 1 over x, comma y, and it tweaked all this data to those points there. One reason that we would suggest doing it, smaller numbers here had to be shifted bigger distances here. And when small numbers shift big differences, that's an inverse relationship. And that tweaked it into a line. Now, I hope I'm not losing you. I'm not asking you to guess that right now. I'm just kind of showing you how I guessed at it. But here's what we got. We could find the slope of that line. It looks like it rose 3 and ran 1, so the slope is 3. And again, in this data, it looks like it graphs and goes through 0, 0, so the y-intercept is 0. So now that we shifted this data into a line and found the slope and intercept, what's the equation of this graph here? Can you see it? Well, what did we graph on the x-axis? Well, it was 1 over x. And 1 over x is what we graphed on the x-axis. The slope was 3, and the intercept was 0, so I'm not even showing adding 0 there. That's the equation that describes this data. Okay. What's beautiful about that is once we have the equation, we can predict. And models that have predictive values are more valuable than models that can't predict things. So if I took data from 1 to 10, but I want to figure out what's going to happen way out here at 24, once I got the equation, I can just plug in 24 for x, multiply by 3, add 0, and it would tell me that y is that variable, that number there, 0.125. Finding data beyond what we measured is called extrapolation, or to extrapolate. Extra is above and beyond. If we wanted to calculate what it was at between 1 and 2, we could, it's just a different method, or just a different term, it's called interpolation, or inside of. We would just plug in 1.5 right there and find out what y is. Okay? But having the equation that describes the relationship gives us predictive value. Typically, all the equations that you look at in physics are going to follow one of 3 different forms. It might be a linear relationship, and we've probably said enough about linear equations. But now let's look at the other 2. The relationship between the variable x and y might be a power relationship, where the variable gets raised to some power and then multiplied by another number. It could be like y equals 5x squared, okay, where a was 5 and b was 2. The third way that it could, the form that it could take on would be an exponential relationship, where y equals a number times a number raised to the variable, where the variable itself is the exponent. Here, the variable got raised to some power. So processes like population growth or radioactive decay often follow this relationship here, where the variable would be time, and that would be exponential growth. So if we had data and we did not know if it's linear, power, or exponential, we could graph it, and if it's a line, well, then it's a linear relationship. If it curves, it might be power, it might be exponential, because both of those have a curve to it. So we have to be able to tweak the data appropriately to turn it into a line. I pause here because I'm on the precipice. To tweak the data appropriately, we have to use logarithms. I know that if you're in geometry or algebra 2 right now, you haven't seen logarithms and you don't know what I'm talking about. If you've already had algebra 2 or pre-calculus, hopefully you are pretty good with logarithms. So if you haven't seen this before, when you get to it in your math class, you'll be able to say, oh yeah, we've done that in physics. But a log is really not that bad. It's just the inverse of an exponent. Let me explain what I mean. If I take log base 10 of 100 and I want to find out what that equals, we could rearrange that. What that means is 10 raised to what number equals 100. So this is just what's called the exponent form, and this is the log form. Anytime we have an equation like this, we could rearrange it into something like this. And this seems to be an easier question. Can you see what x equals? 2? Because 10 squared equals 100. So log base 10 of 100 equals 2. Let's do it here. Log base 2 of 16 equals what? And that's kind of hard to think about. But if we rearrange it and say 2 raised to what number equals 16, then we might be able to solve that problem. Now 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 times 2 times 2 times 2, 4 times, equals 16. So it looks like 2 got raised to the power of 4. X equals 4. We'll do that again. Log base 5 of 125 equals what? I don't know. But if I rearrange it, 5 raised to what number equals 125? Hopefully we can see that x is equal to 3. Because 5 times 5 times 5, 3 times, equals 125. In general, the log of a base of a number equals x can be rearranged into b raised to x equals that number. This was called the log form or the logarithm form, and this was the exponent or the exponential form. So that's what I have right here. One little note on the side is that base 10 is a very common thing. You know, our number system is based on tens. So because it's so common, we can just leave off the 10. We could say log base 10 of a number, or we could just say the log of that number, and we are implying that it's base 10. So here we go. If we take log base 10 of 270, we do that on our calculator. Our calculator is going to give us this number here. And you think, how did the calculator come up with that number? Well, let's see if that number makes sense by switching it from the exponential, from the log form to the exponential form. 10 raised to that number equals that? I'm not sure that makes much more sense, because what does 10 raised to some decimal even mean? Well, we know what 10 raised to the 2 is. That's 10 squared. 10 times 10, that's 100. We know what 10 cubed is. 10 times 10 times 10, that's 1,000. This number here is between 2 and 3. So the answer should be between 100 and 1,000. That kind of gives you some sense of what that means there. Okay, that's just a little introduction into logs. There are 3 general rules that you can use to manipulate logarithms. The first rule is the log of one number times another number is the same thing as the log of one number plus the log of the other number. It's kind of like saying x squared times x cubed is the same thing as x raised to the power of 2 plus 3, or x to the 5th. With exponents, you can add the exponents. It's based on that idea, but that's not a proof. The log of one number divided by another number is the log of one number minus the log of the other number. Okay? And then the last rule that we can use to manipulate logarithms, and hopefully your math teacher will show you the derivation of why these are true. And I know it's not very comfortable to say, just believe me, but all in good time. You'll see why this is true in your math classes. But the log of a number raised to some power, you can take that exponent here and drop it from up here down in front. That's the same thing. We're going to focus in on this rule and this rule to linearize our data. It may have looked like I went off on a little tangent there with logarithms, but now let's come back to how we're going to use that to linearize data. Okay, we know that if you graph x and y and get a straight line, you could find the slope of that line, and that's a. We can find out where it crosses the y-axis, and that's b. Okay, so a is going to equal the slope, and b is the y-intercept. That's it. We can use these functions in a spreadsheet, and let the spreadsheet calculate what the intercept is for me. I'm not going to go into that now, but I will go into that when we do a Excel sheets practice. All right, I think we're good with linear. The trick is, how do we take this and turn it into that so that we can find A and B? So let me hopefully not scare you too much, but we're going to take the log of both sides of this. The log of y equals the log of ax raised to the b. Now we're going to use those 3 rules that were on the previous, or 2 slides earlier. The log of one number times the log of another number is the log of one plus the log of the other. This exponent now can be dropped down in front to right here. Addition can be done in any order. We could take this plus this, or we could take that plus that. We just do it in any order. The beautiful thing about that is that if we graph this on the x-axis, not x, but the log of x, if we graph this on the x-axis, and on the y-axis we don't graph y, we take the log of each y and graph that on the y-axis. What we're graphing on the x-axis has a number being multiplied to it. That will be our slope. What we're graphing on the x-axis has a number added on the end. That number is going to be where it crosses the y-axis. So since log base 10 of a equals the intercept, we can find out what a is by shifting from the log form to the exponential form. 10 raised to the intercept is equal to a. So and then b was the same thing as the slope. So I hope I'm not losing you, but if we graphed x versus y and it curves, we know it's not a linear relationship. But we don't know if it's power because both power and exponential curve. But if I tweak the data, don't graph x, but graph the log of each x. Don't graph y, but graph the log of each y. If we get a straight line here, it tells us it follows this form. And we can find out what A is by doing this, and we can find out what B is by doing that. I'll go over that again, but let's look at, and these are the formulas you could use in a spreadsheet to calculate the slope or the intercept. Let's do the same thing we just did, but now we're going to do it with an exponential relationship, where the variable is the exponent. I'm going to do the same thing I did before. I'm going to take the log of both sides. And then we're going to just apply those rules that help us manipulate logs. That's the log of one number times another number is the log of one plus the log of another. This is an exponent that we can drop down in front. Addition can be done in any order. This plus this is the same thing as this plus that. And then another step we're going to do is multiplication can be done in any order. This times that is the same thing as this times that. What have we accomplished? It's very scary, but what we have found is that if we graph x on the x-axis, if b is a number, the log of b is another number, but it's a number, and that number is going to be the slope. Added on to the end, a is a number, so the log of a is a different number, but it's a number. That number added on to the end is going to be our intercept. So if I graph x versus y and it curves, not linear, it might be power, it might be exponential. But if I don't do anything to the x values, but I do take the log of each y value, then if it turned it into a straight line, it follows this form. And I can find out what a is, because log base 10 of a is the intercept, and log base 10 of b is the slope. I can rearrange it from the log form to the exponent form, and I can find a this way, I can find b this way. This will always be on a spreadsheet that I ask you to do, so you can always refer back to this. But these are the formulas that you can use to calculate b and a. So let me just remind you here that if it's linear, x versus y will give us a straight line. If it's power, the log of x versus the log of y would give us a straight line. If it's exponential, just the value of x against the log of the y's would give us a straight line and would tell us that it's exponential. So here's what we're going to do. We have this data here. We don't know the relationship between those numbers, but we want to see if it's linear, power, or exponential. Let me check to see if it's linear by graphing just those numbers. All these numbers are identical to those numbers. When I graph it, it curves. It's not linear. So now let's go on and check to see if it's power. I'm going to take the log of 1, it's 0. I'm going to take the log of 1.6, it's 0.204. And I'm doing that for all of these numbers there, is what the log of each of those are there. If I graph those numbers, it still curves. So it's not a power relationship. But to check to see if it's exponential, I graph just the x values against the log of the y values, and it did tweak it into a straight line. So seeing a straight line when we graph x versus the log of y tells us that it follows this form, and I can find out what a is by that. Okay, so we can find out what a is by taking 10 to the intercept, highlighting all those data, and plugging it into the function called intercept, taking 10 raised to that answer, and I would find that a is 2. B I can find by taking 10 to the slope. So 10 to the slope of those numbers, and if I did that, I would find that b is 0.8. So graphing it tells it follows this general relationship, but the specific relationship is that a is 2 and b is 0.8. And then I could find out what the value of y was at, say, x equals 10. So we have the equation, we can predict what we're going to get, and that is an introduction into linearizing data.